this reaction up top here actually occurs at quite a significant rate, but it might not actually occur as you might think. Here we have two molecules of nitrogen monoxide gas reacting with one molecule of oxygen gas. Now it appears that three particles all combine at once to give two product particles, but this reaction would not occur at such a significant rate if it required three particles to all collide at once, because it's extremely unlikely that they all collide at one moment and all with the proper orientation. The only explanation for this extremely fairly quick reaction is that it must be actually occurring in multiple steps. Instead of one step, we have multiple steps in our mechanism. For example, it's been observed that or determined that two nitrogen monoxide particles collide with each other to form dinitrogen dioxide. Now this is a reasonable reaction because it only involves two particles colliding at once instead of three. And then this dinitrogen dioxide, which is quite unstable, then further reacts with an oxygen molecule to give two nitrogen dioxides. If you add up these two steps, then you get the following. Now, if you cross out things that are on both sides of the reactants and products sides in equal amounts, then you'll see that the overall reaction is the one provided up top. And so this overall reaction occurs through these two steps. Now, this dinitrogen dioxide, it was formed and then it quickly reacted further. This is called an intermediate. It is a product appearing in the mechanism of the reaction, but not in the overall balanced equation. It's formed and then it further reacts. It exists temporarily. I guess a couple more definitions. There are unimolecular reactions or steps. These involve one reacting particle. For example, we went through an example where uranium-238 decomposed into thorium-234 and an alpha particle. Reactions that are not requiring collisions. There's just one reacting particle. These are unimolecular reactions. Bimolecular reactions involve two particles colliding in a step. So, as an example, two nitrogen dioxides collide, or a dinitrogen dioxide and oxygen molecule collide and react. And then a termolecular reaction, one which involves three reacting particles all at once, is very unlikely. It doesn't occur very much. As our example, we had theoretically two nitrogen monoxide molecules and an oxygen molecule colliding at once. Wow, that is unlikely. Three particles colliding at the proper orientation at once. So, yes, many reactions occur in these multiple steps, and this is kind of the reason that our rate laws are not sometimes the same as the coefficients might suggest. Now, you might have originally thought that our rate law might have nitrogen monoxide concentration squared and then oxygen's concentration to the first power, but actually we see that the rate law for our reaction is rate is equal to K times nitrogen monoxide squared. Oxygen is not involved in the rate law. How can that be? Well, it turns out that only the flow step is the rate determining step in our reactions, and hence we just include this slow step in the rate law. So here, going back to these steps, we saw that this slow one was this first one. And so seeing that, where only those two nitrogen monoxide particles were involved, the rate law is just K times nitrogen monoxide concentration times nitrogen monoxide concentration, or nitrogen monoxide concentration squared. The fast step is not involved in the rate law because, examining here, what determined how quickly our product was formed? The thing that occurred really slowly, very rarely. Once you form this intermediate, it's able to react very quickly. So its brief presence and further reaction doesn't determine how quickly the overall reaction occurs. Now, just theoretically, though, what if instead of having slow then fast here, we had fast and then slow steps? What would be the rate law then? Well, if this first step were the fast one, and then the second step was the slow one, then the rate would be equal to K times the dinitrogen dioxide concentration times the oxygen concentration, as shown here. However, we cannot include intermediate concentrations in the rate laws. We don't know the concentrations of intermediates. We must replace these intermediates with their origins. Now, this dinitrogen dioxide here, which was in our slow step supposedly, this came from the two nitrogen monoxides in this fast step. So we replace our dinitrogen dioxide intermediate with its origins, those two nitrogen monoxides. They gave us that dinitrogen dioxide. And so replacing that dinitrogen dioxide with the nitrogen monoxides, we get this new and different rate law if we had fast and slow instead of the slow and fast. Continuing on another problem, hydrogen peroxide is slow to react, but in the presence of a catalyst like iodide, it actually reacts very quickly, and ultimately it can turn into water and release oxygen gas, or bubbles. Now, this overall reaction then involves this iodide. This iodide is at the beginning of the steps. It's not a product. It's there before the reaction starts. That means that it is a catalyst. A catalyst appears in the mechanism, but not the overall balanced equation. It's present at the beginning of the reaction. It's not a product. Here you can see that if you add up these two steps, iodide is at the beginning, and it's also a product, so it's at the end. It cancels itself out in the overall equation. Similarly, iodide is a product of the first step, but it's used up in the second step. And so it's on the left and right. It cancels. It's not in the overall equation. That's an intermediate. Now, what does this iodide do? Well, it's a catalyst. So we saw our reaction energy diagrams previously, and a catalyst actually lowers the activation energy barrier that you need to go over in order for the reaction to occur. Having a catalyst, having this lower activation energy barrier makes the reaction go a lot more quickly because a lot more particles are able to flow over this lower activation energy barrier. Now, let's talk about rate laws again. It's said that the rate law is equal to K times the hydrogen peroxide concentration times the iodide concentration. If that were the case, then which is the slowest step, the first or the second one? So to solve this problem, you have to say if you had the first step slow and then the second step fast, then the rate law would be equal to the following. We know this because if we had a slow step here, then we would just say the rate law is equal to the concentrations of the reactants in that slow step. So rate would be equal to hydrogen peroxide times iodide times K. If the first step were fast and the second step were slow, then the rate law would be equal to K times hydrogen peroxide concentration times the IO minus concentration. But IO minus is an intermediate, so we would have to replace it with its origins. The origins of the IO minus were hydrogen peroxide and iodide. So replacing hydrogen peroxide, replacing IO minus with hydrogen peroxide and iodide, we would get the following rate law. Okay, so if we had slow then fast step, we would have this rate law. If we had fast then slow step, then we would have this rate law. Now, if the overall rate law is the following, then we must have first a slow, then a fast step. What if it was determined that the rate law was equal to K times hydrogen peroxide concentration squared times iodide? Well, we just learned that having that case means that we have a fast then slow step. So you see that we can determine the order or the speeds of relative steps from the rate laws that are determined experimentally. So you can go from the speeds of each step into the rate law, or you're also able to go from the rate laws into the speed of each step. They give information about each. Thanks for watching, guys.